Hello everyone, my name is Irina Anatolyevna Kudryavtseva. I'm an associate professor and I will be your calculus teacher. I invite you all to join me in learning the fascinating discipline called calculus. I'll acquaint you with many different things that are really used in practice. But as you know, first we should recall main concepts that you came across earlier in your pre-calculus courses. Let's take a look at the diagram. It contains the main topics we will learn in our course. I want to notice that the course is 2 semesters long. That implies the division of our course into 2 parts, part 1 and part 2. During the first semester, we will try to introduce such concepts as functions of one variable, limits, continuity, and also we will improve our skills in differentiation and integration. Sometimes students don't observe integrals in schools. So I'll start with construction of some analogy between differentiation and integration. And I hope it will help us to get over difficulties if they appear. When observing the topic differential calculus, we won't apply basic rule of differentiation only, but we will consider new approaches, for example, the logarithmic differentiation. Also, we will familiarize with high-order derivatives and try to use them in order to approximate functions by polynomials called the Taylor polynomials and Maclaurin polynomials. We will learn how to sketch graphs utilizing derivatives. Our next part, the next semester, will be dedicated to the multivariable calculus. We will introduce n-dimensional space, functions of several variables whose domain is a subset of the n-dimensional space. We will adhere to the study plan of the first semester for the single variable case, and we will reveal the concept of limit. However, there may appear some difficulties to calculate limits, and the techniques that work for functions of a single variable fail here. Then we will observe what partial derivatives are and what the integral with respect to a measure means. Oh, I said a lot, and most of the things were difficult for understanding. Don't worry, I promise all mentioned above will be clear with the passing time. In conclusion, I'd like to pay our attention on the references presented on the screen. The first 6 points are textbooks written by Russian authors. They are published only in Russian, so it may be a good reason to improve your skills in learning Russian. This page presents works in English. All of these textbooks contain main theoretical aspects complemented by practical examples, and I'll borrow some examples from these sources often enough. Today, we will talk about sets. We will consider operations on sets. We will recall particular case of sets, number sets, the set of natural numbers, the set of integer numbers, the set of real numbers. We will show how to convert a verbal description into a mathematical expression using mathematical symbols. Maybe most of what I'll say are familiarized, but I wish to systematize our pre-calculus knowledge. Let's begin with some basic notion and notations. The most basic notion is the set. What is a set? It can be defined in such a way that any object is either in the set or not in the set. For example, a collection of stars in the sky, or for example, the collection of solutions of the following quadratic equation x squared minus 5x plus 6 is equal to 0. Or, for example, all negative real numbers, all, I don't know, for example, the set of natural numbers. A set is usually denoted by capital letters, capital A, capital B, capital C, while objects which compose a set are denoted by lowercase letters, A, B, C, and so on. The objects are called members or elements of a set. And one more interesting definition, the set with no elements is called the empty set, and it is denoted as 0 because, as you see, our set has no elements. It can be helpful to use Venn diagrams when operating with sets. In the Venn diagrams, the universal set, capital U, is presented by a rectangle, and all other sets are represented by circles or any closed region into this rectangle. Well, as we see, there are two sets, capital A and capital B, contained into our rectangle that represents the universal set capital U. So maybe we run before we can work, but I can help saying that if we see such a location of sets, that means A and B are subsets of our universal set capital U. And I think you've guessed that A is a subset of B because our B contains A. Now, consider one more interesting relation that indicates set membership. This relation is interpreted as is element of. I'm talking about this symbol that looks like the Greek letter epsilon. Elements are depicted by points on the Venn diagrams. Thus, the element A belongs to the set B. The negation of set membership should be read as is not element of or doesn't belong to. Hence, the element A doesn't belong to the set A. Since the set A is a subset of the set B, the element B is an element of our set B as well, because all elements of A are elements of B. In this line of thoughts, we can say that the element C belongs to neither A nor B, but it is an element of the universal set U. How can we specify sets? There are two ways of specification. The first way is to list all elements that are contained in a set. The second way is to define some rule that characterizes a set. By the way, when we list elements, we separate them by commas and enclose in braces or curly brackets. Let's make an example. The problem is to define the set of solutions of the quadratic equation x squared minus 5x plus 6 is equal to 0 using both ways of specification. First of all, we should find roots of the given equation. Of course, it's obvious that these are 2 and 3. So, according to the first way of specification, we should put a letter used for a considered set, in our case capital A, then write the equality sign, then put the opening curly bracket, and then list all elements that are in our set, and then put the closing curly bracket. Using the second way, we should place a rule into the curly brackets. The given representation can be read as follows. The set A contains elements X, and here, look at this, look at the screen, we see a vertical line, and this vertical line should be interpreted as such that. So, once again, the set A contains elements X such that x squared minus 5x plus 6 is equal to 0. So if we take some element x and substitute it for x into our equation, we will get the identity. Now, we can give this strict mathematical definition of a subset. Well, a set A is said to be a subset of a set capital B, and noted as you see on the screen, if every element of the set A is an element of the set B. One more definition. The sets A and B are said to be equal if and only if A is a subset of B and B is a subset of A at the same time. I'd like to focus your attention on the notation for a subset of some set. In the definition on the top of the page, the set A and the set B might be equal. If A is a subset of B, but A is not equal to B, we say that A is a proper subset of B. In this case, we remove the low line in the notation. Now, let's take a look at this screen again and consider the following three sets. The set A, our set, is a set of 5 elements. This set contains 5 elements, 1, 2, 3, 4, and 5. The next set, B, includes 3 elements, 1, 3, and 4. And here, as you see, we use the first way of specification. And finally, our set C includes 5 elements, 2, 3, 1, 4, and 5. And here we can conclude that the set B is a proper set of A because B is a part of A. Yeah? But C, we see that our set C includes the same elements. If we compare these elements with elements of our set A, and we can notice that C is a subset of A, not proper subset, but a subset of A. Now, let's talk about sets, set operations. And the first operation is the union of sets. Well, let's give the definition for the union of two sets. The union of two sets, capital A and capital B, or A union B, is a set of elements that belong to A or B. To visualize results of operations on sets, the Venn diagrams can be used. So, let's draw some rectangle. This rectangle is our universal set, capital U. And let's draw 2 more circles that are our set A and our set B. And our result should be shaded. Yeah? We need to shade both A, the common part, and our set B. The next operation is the intersection. Well, the intersection of two sets, A and B, or A intersection B, is a set of elements that belong to both A and B. So, for this operation, we need to take some common part of two sets. If our sets are isolated, there is no common part, and our intersection is the empty set. Well, let's consider two more operations, the relative complement and the absolute complement. The relative complement of A in B, or B minus A, is a set of all elements that don't belong to A but belong to B. For the relative complement, we shade the part of B that is not common with A. The absolute complement of A in the universal set U is a set of all elements that don't belong to A. This absolute complement should be read as not A. For the absolute complement, we take all elements that are not in A. The considered operations have a variety of important properties. Let capital U be the universal set, and capital A, capital B, capital C are subsets of our universal set, capital U. Then, for example, A union B is equal to B union A. A intersection B is equal to B intersection A. This property is called the commutative law. The next property, A union the empty set, results in our given set A. Or, for example, A intersection A is A, A intersection the universal set is A, and these two properties are called the identity law. Then we can consider the idempotent law, then the domination law, associative law, distributive law, involution law, and the De Morgan law. Well, for example, A union B union C is A union B union C. Or A union B intersection C is equal to A union B intersection A union C. Or, for example, not A intersection B is equal to not A union not B. We can draw the parallel between the union operation and the intersection operation and operations on numbers. For example, if we consider the first operation, I mean A union B is B union A, or A intersection B is B intersection A, it is equivalent the following. A plus B is equal to B plus A, and A times B, or A is multiplied by B, is equal to B times A. Each of the presented properties can be proved with the use of the Venn diagram depicted for two sides of some given expression, or we can do with formal reasoning. Well, let's consider one more property. I'm talking about the De Morgan's law, property 8. Not A, and let's prove this property. Not A union B is not A intersection not B. Let's try to prove this identity. Probably last time I said the inequality, of course, it's a mistake because, of course, we are talking about identities. Well, let's keep the same strategy as in the previous example. And now let X be an element of our left-hand side, or X belongs to not A union B. Well, it means that X belongs to the universal set and X doesn't belong to A union B. Well, this implies that X belongs to the universal set and X belongs to not A and X belongs to not B. Oh, here we can add one more step and say that X belongs to the universal set and X doesn't belong to A and X doesn't belong to B. Of course, the last phrase is equivalent to the following construction. Yeah? X belongs to not A and X belongs to not B. So our X belongs to not A intersection not B, and our not A union B is a subset of not A intersection not B. Now, the next step is to prove that the right-hand side is a subset of the left-hand side. So, let X be an element of the right-hand side, or not A intersection not B. Well, this implies that X belongs to not A and X belongs to not B. O X belongs to U and X doesn't belong to A. O X doesn't belong to doesn't belong to B without this line, of course. And the final statement implies that X doesn't belong to A, O, B, A union B. O, X belongs to not A union B. Well, and it means that our not A intersection not B is a subset of the left-hand side, not A union B. Let's make one more example. We need to prove the following identity. This time I'll use the Venn diagrams to show that this identity is true. Maybe last time I said the inequality, but of course it's a mistake because we are talking about identities. Well, now let's consider our left-hand side and try to find the result of this given operation. Well, first of all, let's draw some rectangle. This is our universal set. And two more sets, capital A and capital B. Now, let's take a look at this operation, A intersection B. So A intersection B gives us the common part of these given two sets. So with this common part, of course, we need to shade this region. Now, let's consider this operation, A intersection not B. And of course, first of all, we need to identify the result of this operation not B. Not B is a set of all elements that are not in B, yeah? these elements are in U, but not in B. And we need to consider this part of our picture. Now, we need to take the common part of our set A and this shaded region, this not B. Of course, this common part is this part of A. This part of A. And now let's add, look at this, our next operation, our final operation. We need to find the union of this set and this part. And of course, the result is our given set A. A is our result. A. Once again, the left-hand side is the given set A. Now, let's work with the right-hand side and draw this similar rectangle again. This is our universal set here. Then our two sets, capital A and capital B. And now our first operation is A union B. A union B is a set of elements that are in A or in B. And our region looks like this. This is A union B. Well, now let's consider this operation, A union not B. Well, we got this set not B. Not B is a set of elements that are in U, but not in B. Well, now we need to take the union, yeah? Our set A and not B. Well, of course, we have this set. We have A. And finally, we need to take the intersection. This operation and this result. And finally, we will have the same. We will have this set A. And look at this. Here we have A, and here we have A as well. So this identity is true. But the Venn diagrams cannot be used as the formal proof, as a formal proof. Only we can use them only as an illustration because, for example, we don't consider different relative positions of our sets A and B. We said earlier that the mentioned properties of set operations can be proved using formal reasoning. Let's show how it works. And let's consider property 6 as an illustration. So, according to this property, A union B intersection C is A union B intersection A union C. First of all, we need to show that my left-hand side is a subset of the right-hand side. Let's put our first point. A union B intersection C is a subset of my right-hand side, A union B, intersection A union C. Indeed, if X belongs to our left side, A union B intersection C, it means that X belongs to A, X belongs to B, and X belongs to C. If X belongs to A, then X belongs to A union B, and X belongs to A union C. But the last statement means that X belongs to A union B intersection A union C. And we can conclude that this set, my left-hand side, A union B intersection C, is a subset of the right-hand side, A union B intersection A union C. That was to be proved. So let's move on to the next point and show that my right-hand side is a subset of my left-hand side. Well, now our next point. We need to prove that A union B intersection A union C is a subset of A union B intersection C. Let X be an element of the right-hand side of A union B intersection A union C. Then this assumption implies that X belongs to A union B and X belongs to A union C. Well, it means that X is an element of A, X belongs to B, and X belongs to C. And now, this statement implies that X belongs to A union B intersection C. Well, and this result is the same as A union B intersection. A union C is a subset of the left-hand side A union B intersection C. So this inequality is true.